his reward to him.
We've all seen Spider-Man as kids. You know, the boy who swings from buildings in a tight blue and red suit. Have you ever wondered if all of his tricks and flips are physically possible? Well, in this edition of Mythbusters, we will be testing out whether or not some of his jumping sequences are actually real. Let's start by looking at that intro video one more time. Now, before we can actually analyze the Spider-Man video, we need to know a little bit more about projectile motion in general. Projectile motion is defined as something flying through the air under the influence of gravity. The motion of that thing, in this case Spider-Man, is split up into two different directions, one horizontal and one vertical. In a real-life scenario, there should be no horizontal acceleration, and the velocity of an object should be constant because the horizontal forces acting upon the object are balanced. This translates into a linear equation on position versus time graph. The vertical direction is a little bit more tricky. In projectile motion, the object should be accelerating when going through the air. This is because the forces acting upon the object are unbalanced, and unbalanced forces equal non-constant velocity. Let's relate this back to the Spider-Man video. After Spider-Man jumps off the building, the force applied to him that made him jump is no longer being applied, and the second that he jumps off the building, the forces being applied to him are unbalanced. In addition, after jumping, gravity would be the only force applied to him, which would in turn make him slow down. His vertical velocity would constantly decrease until a point in which it would reach zero. After this point, the situation is similar to when something falls only with the vertical component. As his position decreases as far as moving away from zero, his velocity should increase. Here's a position versus time graph and velocity versus time graph of what this should look like.
Kane is in the building.
Now that we know more about projectile motion, we can begin to analyze the Spider-Man video. Using Logger Pro, we can examine his fall and calculate velocity versus time graphs. Now, here are the graphs that represent Spider-Man's fall. Now is time for the busting. From the position versus time graph, we can see that in the horizontal direction, the velocity of Spider-Man was constant, because the line representing the horizontal motion is linear. In the vertical direction, Spider-Man's velocity was not constant, but he was accelerating at a constant rate. This is portrayed in the position versus time graph because the line representing the vertical motion is parabolic, meaning that it is shaped like a parabola. These things can also be seen on the velocity versus time graph. The line representing the horizontal motion is parallel to the x-axis, meaning that the velocity was constant the whole time that Spider-Man was falling. Vertically, the motion of Spider-Man is represented by a linear line because he was accelerating in a vertical direction. Another thing to note is that the velocity of the horizontal motion is negative because Spider-Man is moving away from zero. This, though, only has to do with where the origin is placed. Thus far, the Spider-Man jump is proven to be accurate because the shapes of the graph are similar to what the shapes of a real-life projectile would look like. We have yet to do calculations. To find whether or not this fall is true, we have to start by first looking at the table representing his motion. Because the motion of the projectile is split up into two different directions, we can't use one equation. Instead, we have to use two separate equations. The only thing that is the same within these two equations is the time variable. In order to find out if the Spider-Man jump is real or not, we need to plug in using the normal acceleration of an object that is only under the influence of gravity. This number is 10. We also need to plug in for how far the object has fallen, or its displacement. This is where the table comes into hand. If we subtract the first value representing vertical motion from the last value representing vertical motion, we can see how many meters the object fell. After finding that number out, we can then plug into the equation that is used to find vertical displacement, but instead of solving for displacement, we will be solving for time. Let's do that and then discuss the horizontal motion. Now that we have found the time variable, we can plug it into the equation for finding the horizontal displacement. Remember that these answers are only valid if the Spider-Man fall is physically accurate. We now must go back into the graphs and see whether or not Spider-Man was able to travel the total displacement indicated by the table in 0.83 seconds. We can also look at the table representing horizontal motion and find what the actual displacement was by subtracting the minimum value from the maximum value. If this number does not match up to the one that we found using the equation, then we know that this is not an accurate fall. and it appears as though it took Spider-Man somewhere over 1.6 seconds to fall, meaning that he was accelerating at a way slower rate than what one should in projectile motion. Earlier we found out using the equations that Spider-Man's horizontal displacement should have been 8.3 meters. But if we look at the table, his horizontal displacement was only 3.37 meters, again proving that he was going way slower than physically possible for a projectile. And there you have it, people, Spider-Man has been busted.